Good day. This lesson is the fourth part of line integrals. It is about the independence of path and test for conservative field. Here are the objectives of this lesson. At the end of this lesson, you are expected to evaluate line integrals using two paths of integration and identify a conservative field and its associated potential function. In this lesson, we will be evaluating line integrals of the form integral of f of xy dw along the curve C, where f of xy dw has the form f sub 1 dx plus f sub 2 dy. This is a combination of the cases dx and dy. Dx and dy here are the two paths of integration that we will be dealing with. We have here the definition of independence of path of three space. It says here, the line integral of a vector function f equals p of I plus qj plus rk is said to be path independent if and only if p, q, and r are continuous in a domain D, and if there exists some scalar function u equals u of x, y, z in D, such that f equals grad of u. Grad is also gradient. Or we have p equals the partial derivative of u with respect to x, then function q is equal to partial u with respect to y, and function r is equal to partial derivative of u with respect to z. If this is the case, then the line integral of f along the curve C from A to B is given by the formula the integral of f of r dot dr along the curve C is equal to the integral of p of dx or p times dx plus q times dy plus r times dz along the curve C is equal to u of b minus u of a. This result for line integrals is analogous to the fundamental theorem of calculus for functions of one variable. Hence, if the line integral is path independent, then for any closed contour C, we have the following integral notation. So this is called superimposed integral. So we have here now the integral of f of r dot dr. A vector field of the form f equals grad u is called a conservative field, and the function u is equal to u of xyz is called a scalar potential. This slide shows the test for conservative field of function in free space. So it says here, the line integral of a vector function f equals pi plus qj plus rk is path independent if and only if f is equal to, we have the determinant, which is a 3 by 3 matrix, is equal to 0. So we can find the determinant of this matrix by basket method or the cofactor expansion about a row or column. It is implied that each component of f has continuous partial derivatives of variables x, y, and z. Then we have here the independence of path and test for conservative field for two space. It says here, if the line integral is taken in the xy plane, then the following formula is valid. We have the integral of p dx plus q dy is equal to u of b minus u of a. In this case, the test for determining if a vector field is conservative can be written in the form partial derivative of p with respect to y is equal to partial derivative of u with respect to x. The considered test is the necessary requirement, but generally speaking, it is not sufficient condition for a vector field to be conservative. However, this test is sufficient if the region of integration D is simply connected. Let us have the following examples. It says here, evaluate the line integral of x plus y dx plus x dy along the curve C for two paths of integration. So we have letter A, the curve C is the line segment from A with coordinates 0, 0 to B with coordinates 1, 1. And letter B, we have the curve C is the parabola y equals x squared from A whose coordinates are 0, 0 to B whose coordinates are 1, 1. Determine also if the vector field is conservative. So first thing to do is to find your vector field F. And we can define the vector field F by writing it as F of xy is equal to x plus y, referring to the first integral given, or we have x plus y. Then we have the second integral, which is x. Let me erase this part. So we have this as x. Then let us now evaluate the given integral. So that is the integral of quantity x plus y dx plus you have x dy along the curve C. So let us define first what is y, because we need to have this variable y replaced by x because the variable of integration of dx. Likewise, we're going to replace dy with dx. So our y here can be found from the line segment whose 2 points are given. So we have here, the 2 points are given as, we have the coordinates 0, 0, and 1, 1. If we're going to plot it, so we have this as now the point A and point B. Suppose this is your 1, 1. Let us define the equation of this line. The equation of this line can be found by the formula of a line using the points law form. So we have y minus y1 equals m times x minus x1. So let us define first the slope. This slope can be found by, we have it as y2 minus y1 all over x2 minus x1, where we can easily see that we have this as our x1, y1, which is the first point, and x2, y2, which will be the second point. So computing now for the slope, we have it as your y2 is 1, y1 is 0. While we have x2 is 1 and x1 is 0. So this slope is equal to 1. And defining the equation of the line, so let us use the point 0, 0. At point 0, 0, we have here now y minus 0 equals m, which is 1, times x minus 0. Or simply, this is y equals x. So we have found now the value for y, or the replacement for y in terms of x. And for the replacement of the differential y or dy, so let us get a differential of your y equals x here. So differential y equals dx. So this will now be replaced by, we have here the integral of quantity x plus x dx, plus we have here x, and we have dy is dx along the curve C. Then we can rewrite the whole integral as the quantity x plus x dx. What about the limit? So we can find the limit from the given coordinates of your 2 points A and B. So that is, we get the x coordinates. So that is abscissa right, which is B, which is equal to 1, and abscissa left is 0. So we write here as 0, 1. So we're going to evaluate this now. We have here x plus x plus x is 3x. dx from 0 to 1. Integrating this now, we have it as 3x squared over 2 from 0 to 1. Applying the limits, we have 3 halves. Then let's replace x by 1. That is quantity 1 squared. And we have the lower limit, which is 0. That is quantity 0 squared. So evaluating this will give us 1 times 3 halves. The answer is 3 halves. Next, if we're going to determine if the vector field is conservative, so what we will use is the test that the partial derivative of the function p with respect to x is equal to the partial derivative of the function q with respect to, this should be y, and this is with respect to x. So this is testing if the vector field is conservative. So let us get your partial derivative of the function p with respect to y. Where is your function p? Your function p is right here. We have it as x plus y. And your function q, we have this as x. So getting the partial derivative of p with respect to y, the answer here is 1. Why? Because the partial derivative of x with respect to y is 0 because x is constant, while we have y is 1. Then the partial derivative of your function q with respect to x. So since this is our q, differentiating with respect to x, that is also equal to 1. So since the values of the two partials are equal, so we can say now that the vector field is conservative. So let me write here, if vector field is conservative. So therefore, your conclusion is vector field is conservative. So this is how we answer letter A. Let us solve for letter B. For letter B, let us use the same integral given. So we have the integral of quantity x plus y dx plus we have x dy evaluated along the curve C. So again, this will be your function p, and this will be your function q. So what we're going to do is to replace y with the given equation of your parabola. which is x squared. So this can also now be written as the quantity integral of the quantity x plus x squared dx. Then plus we have x. And dy here can be found by getting the derivative of your parabola, which is y equals x squared. Or I should say differential. So the differential now of y is dy, while the differential of x squared is 2x dx. So we can now replace dy with quantity 2x dx along the curve C. Then what we will do is to combine now the quantity x plus x squared plus we have here 2x squared. Then dx. Then same limits will be used. That is, we have here, since the variable of integration is with respect to x, so we will use the x coordinates from these 2 points. We have 0 and 1. So evaluating this, we have here now, simplifying your expression here, that is quantity x plus 3x squared dx from 0 to 1. So integrating now, we have this as integral of x dx is x squared over 2 plus we have here 3x cubed over 3 from 0 to 1. Simplifying this, we have it as cancelled. And applying the limits, we have here now quantity 1 squared over 2 plus we have quantity 1 cubed. While the lower limit will give us 0 squared over 2 is 0. 0 cubed is also 0. So this gives us 0. When we now simplify further, this is 1/2 plus 1, which will give us 3 over 2. Observe that the value that we obtained in both A and B are equal to or is equal to 3/2. So with that, we can now test if the vector field is conservative. So that is, again, by defining your P, if we have the partial derivative of your function P with respect to y is equal to the partial derivative of Q with respect to x. So this is testing for the vector field if it is conservative. So the derivative of x plus y with respect to y is 1. Then the derivative of or partial derivative of the function q with respect to x is equal to 1. Since they are equal, we can say that the vector field is conservative. So this is the answer for this problem, letter B.